Yep.
Thank you. So basically, some general information I'm gonna provide. So first, um, because some students they got some special extension by professor or by me. So basically, their homework too maybe are still not handed in. So that means right now I cannot post the solution to the homework, but I will post homework solution once everybody like hands in their homework assignment. Yeah, I know it's kind of frustrating because you all of you want to like check like where you did the homework wrong or like um, make the homework as one of your key review materials. But I will guarantee like before midterm exam and before final exam, you'll get like all the homework solutions accordingly prior to midterm exam and prior to final exam. So you can review your homework before the exam. And I will try to post the solution as soon as possible. Um, so I think we can get started on homework 3, I guess.
I have a question. Can you go over number 2?
Yep.
Okay.
I was also confused on number two. I didn't really understand what the question was asking.
Yeah, me too.
Okay, so basically you're gonna show, I mean, you don't have to strictly prove, but you're gonna show that um, two independent, like you have two independent exponential distribution, and basically the multiplication of that two distributions is still an exponential distribution, right? You have two atoms, and uh, and I guess in lecture you kind of covered like a basic trait trait of the exponential distribution is the probability that an atom surviving time t is just e to the negative lambda t, right? It's independent of what has happened before. It's only related to that time t. And now you have two atoms. So basically, you're gonna show what's the probability that both of them survive in time t, right? So you just multiply those two functions together, those two probability, which is essentially the same. Like you multiply those two probability together, and you get a new probability function, which is the probability of two atoms, uh, both surviving time t. And you discover that is in fact another like exponential distribution with parameter 2 lambda. And the basic, I think the basic idea of this question is for exponential distribution, right? e to the power of a times e to the power of b is just e to the power of a plus b. That's the basic idea of this question. And here it's just like e to the power of negative lambda times e to the power of negative lambda is just e to the power of negative 2 lambda, something like this. And because those two atoms are independent, so all the probability you want to find, you're just gonna multiply those two probabilities separately because they're two independent event. And so basically that's the idea. Like you don't have to strictly prove anything. You don't like to write fancy language to prove, but you just, I mean, you're just gonna show some basic, I don't know, some basic trait of the exponential distribution. And yeah, Russell.
Thank you very much for the explanation. I mean, it makes sense. The only confusion I had on it was that Professor Bartman mentioned that we would have to use calculus for number two. So I assume that we would be taking the density function and finding the integral of it. But your explanation makes sense as well. So I'm just wondering what the difference between the two methods is.
Yeah. If you want to challenge yourself, you can go back to the class slides, right? In class slides, I guess it's named probability, some basic probability something. It's one of the first 2 or 3 documentations that was uploaded on Brightspace, and it has like 5 distribution. I guess like binomial, hypergeometric, Poisson, right? And they have exponential distribution, and it has 2 slides actually. Has 2 slides. And they have some calculation, so some calculus things, some integral, and you're gonna use some limits and integral to derive what I have just said, that the probability of an atom surviving time t is e to the negative lambda t. The tricky part is how you derive that e to the negative lambda t, which is the probability mass function, and but I guess you don't have to. You have to do that. You don't have to do that calculus from the base ground. Like I assume you can use that probability mass function, the e to the negative lambda t, and you can do whatever left. So you don't have to prove that probability mass function. Yeah, Vivian.
I was just wondering like how you knew for sure that it was independent, because I remember like in the textbook it said that like independence can only be calculated. So I was wondering like how you like knew that it was independent without calculating it.
Sure. So I have 2 atoms, as well as the outcome of atom number 1 will not influence the outcome of atom number 2. Then it's independent. Like I'm tossing 2 coins, or for example, I'm tossing 1 coin twice. The outcome of the first result will have no influence on the outcome of the second result. Then those 2 events are independent. And what you have said without calculation is something from our basic physical sense, from our basic sense, you cannot determine if 2 events are independent or not. Then you have to calculate the probability and see if it matches the probability of, A intersect B is exactly the probability of A times the probability of B. Then that shows you independence. But in some events where from your physical sense you can directly know if it's independent or not, then you don't have to calculate.
Yeah, thank you.
Other questions?
I was also wondering, just for the future, for the midterm and the final,
Yep.
how similar those questions will be to, for example, homework questions, and if there's anything that we don't cover in class that we should know for those exams.
Then how come these 2 are equivalent but now make 26?
I think no. Like everything from class would be sufficiently enough for the exam. Yes. Like for the first exam, you're gonna do something about probability distribution. Like I mentioned, that 5 probability distribution in class slides. 5 or 4, I think there's binomial, hypergeometric, Poisson, exponential, and uniform. So we have five probability distribution, and then you're gonna learn some central limit theorem. It would be gonna be tested in exam, and I think some t-tests. I don't know if you guys have started some hypothesis testing, but yeah, those may also appear during the exam. But right now, like the most important is the probability distribution.
Thank you.
Yeah, Mariam.
I had a question about the first question. So I tried to find lambda by multiplying each number of hits to the number of sectors and then dividing it by 576. But then the answer that I got was 0.928. And when I tried putting that into Minitab, it said that for a Poisson distribution, the mean needs to be between 1 and 709, I think. And I tried to resolve it a couple of times, but I wasn't sure where I was going wrong.
Miriam, you have to add 229 to that because although it's 0 hits, it's still a part of the average. So it's all of that multiplication plus 229 over 576.
Oh, okay. Thank you so much.
Yeah.
Yeah. And basically the Poisson distribution is an extreme situation of a binomial distribution, right? Just it has a very low probability of success and a very large sample space. Like for a standard binomial distribution, like you're gonna toss, I assume like you're gonna toss 10 coins, and the probability of getting a head equals the probability of getting a tail, which is 1/2, right? So basically a binomial distribution doesn't require a large sample size. You can toss 10 coins, you can toss 5 coins. It can be a very small sample size, and the probability can be relatively large. And in this case, 1/2 for each outcome. That's the tossing coin example. But for Poisson distribution, you should have a very large sample size. And in this case, it's the number of hitting, right? So basically, you're gonna use 229 times 211 times 1 plus 93 times 2, right, all the way to 5. That's the last one, right? You have 5 locations. You have 1 locations which get 5 hittings. So that's the total number of hitting. And the possibility of hitting a specific sector, the p is very small. It's just 1 divided by how many sectors you have. And in this case, it's 1 divided by 576, right? So you see kind of here you have a very, very large sample size, and the probability is very, very low. And solving this problem is like you're tossing 535 coins, and each time the probability of getting ahead is just 1 over 576. And you're gonna calculate what's the probability of getting 0 head, what's the probability of 1 head, of 2 heads, of 3 heads, right? And you can definitely do this applying the formula of binomial distribution. However, the Poisson distribution has like a more efficient formula, which is you do some limit calculation. When you first you use the formula of binomial distribution, and when the sample size n approaches infinity, and when the probability p approaches 0, then and do some limit calculation and algebra, then you can derive the Poisson distribution formula, which is I guess is like lambda to the power of to the power of number of success divided by that number of success factorial times e to the negative lambda, right? That's the probability mass function for Poisson distribution. And where lambda is just n times p, right? So kind of, I think just Russell just explained how to calculate that lambda, how to find that n. You're gonna add the side of 0 hits. And so basically just assume the bombs are landing at random, so which gives you what I just explained, and you calculate the theoretical frequency of hittings provided the bombs are landing at random. So you calculate the theoretical frequency, and then you compare that theoretical frequency to what have actually happened, and you see if there's a large discrepancy. If there's a large discrepancy, then probably the bombs are not landing at random. But if the theoretical frequency about the same as the data set in your homework assignment, then that gives you a hint that basically the bombs are just landing at random. Yes, Vivian?
Wait, how do you calculate lambda using n times p? Because I did like the total number of events divided by like n. Does that work too?
Yeah, wait, is lambda not 0.9288?
Yeah, because that's what I got, and then I like put it in the formula.
I don't know the exact number. I didn't do the calculation, but basically lambda is n times p, right? And what is n? N is the total number of hitting. The total number of hitting. How many bombs in total? That is your n. And what is p? P is a possibility of hitting a specific sector, which is if you assume that bombs are landing at random, that p equals 1 divided by the number of sectors, right? That's the probability, and lambda is just n times p. I don't know if that's 0.92 or something, like I didn't do it, but that's the idea, yeah.
Can you do it the other way with like k over n? Like, does that work too? Or do you have to do it as like n times p?
I don't know what's the k. What do you mean?
Like the total number of events? Like I did it the way that Miriam did it with like 0 times 229 plus 1 times 211 and like so on. And then I got 535 divided by 576 to get lambda, but I don't know if I did that.
Yeah, that's true.
Wait, so is 535 the number of hits, and then you multiply that times 1 over 576? Is that what you do?
So both of you
Okay,
are
so then,
saying the
yeah,
same
okay.
thing. Yeah, you're
Okay,
saying
yeah,
the
it
same
is the
thing.
same thing.
Okay, yeah, it's the same.
Wait, no, isn't it a fee? It's a
Yeah.
fee.
To me, it's a shame. I didn't choose it, but I just ended up there.
That's hard.
No one in my room like does music.
Just one roommate?
I have one roommate and 3 suitemates. Like
Like 2-2?
For the midterm, so we're supposed to know how to use Minitab, right?
Never my dorm. I'm always like out.
No,
Yeah,
no.
you're
Like you don't really have to play with like Minitab right now. Even for the final exam, you don't have to use Minitab. Like all the information will be provided. Like you don't have to calculate what's this standard deviation of some data. You don't have to do that. It's provided on exam paper.
Okay, thank you.
In class today, like he used like a normal distribution table. So like do we have that table like provided, or do we need to like
Yes.
Okay.
In exam, like the table is provided. But you're gonna know how to use that table, right? You're gonna like you have to because in the table there's always there's always 2 axes. Like one axis is the number of observation or the sample size, and another axis is the degrees of freedom. So and degrees of freedom is kind of important for you to locate the data you want to locate in that table, right? So for all the questions, you have to calculate the degrees of freedom by yourself. And right now, it's kind of easy. Like for most distribution, it's just a -1, something like that. But later on, when you have T distributions, when you have F distributions, the degrees of freedom becomes more complicated. So that's something you have to notice. Like even though the table is provided, you still have to do some calculations to locate the number in the table.
Victor, so I was just wondering if you could clarify on this point. If the theoretical probability matches what actually occurred, that means that it's targeted, right?
No, that means it's not targeted.
Can you clarify that?
Because my assumption is P equals 1 over 576, right? That's my assumption. What does that mean? That means the probability when the bombs are landing at random. That's my, so based on that assumption, I have my P, I have my lambda, I have all my calculations later on. And if my theoretical frequency coincides with the table that you've been provided, then that means my assumption is correct. My assumption actually makes sense. So the bombs are really land at random. But if my theoretical frequency has a huge discrepancy from the real data, then that means my assumption actually doesn't make sense and the bombs are not landing at random. So that's the logic. Yeah.
I understand. So when we use the Poisson calculation, we're we're finding the probability that it's random, right? Thank you.
Yeah.
Hey, Victor, I had a question on at least the first one. So
Go ahead.
I know it's a Poisson, but usually when I like try justifying it's a Poisson, I say that's like large sample size or like a small probability of success. However, in this case, you don't really know the probability of success at this point, right? Or does it just be 1 over 576?
Yeah, so basically you assume it's 1 over 576, right? And your assumption
Okay.
is the bombs are actually landing at random. So based on
Yeah.
that assumption, you have P equals 1 over 576. So
And then
yeah,
you can justify it through that.
yeah, so that gives you a sufficiently small P,
Oh,
which
okay.
gives you a right to use the Poisson distribution. Yeah.
Okay, that makes sense. Thank you.
Hi, Victor. After we've finished finding out like the theoretical probabilities, it asks what you can say about the targeting process. So, do we base that answer on our findings of the probabilities?
Yeah, I think yes.
Okay.
And we still assume it's at random, right?
Yeah.
Okay.
It's
Okay.
true. I mean, for most problem, right? So for most problem, it's, I don't know. Even in the exam, I think the questions is not formed this way. Like for most question, it would give you like, now I have a Poisson distribution, which is being studied, being justified. It is a Poisson distribution. And then I'm gonna ask you to find some probability, right? That's a normal setup of like a question in Poisson distribution. But in this case, it just like gives you some reverse information. It gives you the probability that have been calculated, but didn't tell you if that's a Poisson distribution or not, right? So what you're gonna do is first, I assume it is a Poisson distribution, and then I calculate my theoretical probability and see if that matches the data being given. And if it matches, then I say my assumption is justified. Yeah, any other questions? Any kind of question? Like not necessarily
Oh, I've had
homework too. Yep.
one more question, but this is more about question 2.
Yep.
So I kind of figured out the initial form for at least the first decay, which is an exponential. So I said it'd be 1 minus e to the negative lambda x.
Yep.
But then after that, like I got confused on how would you show the time until the disintegration occurs again with parameter 2 lambda.
Okay, so first it's not like decay again. Like one atom can only decay one time. So basically you have two separate atoms. And
Okay.
that's the first problem. And second, I guess a easier way is not like 1 minus e to the negative lambda x. You just use e to the negative lambda x. And that gives you the probability of that atom surviving time t, which means like at time t, it still doesn't decay. And that gives you that probability mass function, right? And then
Yeah.
you have the second atom with exactly the same probability mass function. And then you just multiply those two together and you can get something similar, but you have a parameter of 2 lambda. And
Okay.
and using that, right? Using that, it's sufficient to show like it's still an exponential distribution. But if you are interested, you want to challenge yourself, you can use that probability mass function, and you can actually derive like the probability density function. You can derive like what's in the slide, like some integral stuff.
Yeah. Because I did that initially, but that led me to the 1 minus e to negative lambda x. But I get it now. So you can just multiply the two probability functions of the e to negative lambda x, and then it'll come up with the parameter negative 2 lambda.
Yes, I think
Okay.
it would be sufficient. Yeah.
Oh, okay. Thank you.
Wait, I'm sorry. I just want to like clarify this. So if like our theoretical frequencies match up with like the data that we get, does that mean it's random then? Or I don't know. Kind of confused.
Yeah, so you have p equals 1 over 576. That's based on your assumption of randomness, right? Only when the bombs land at random do I have the probability p, which is 1 over 576. And then I use that p to calculate my lambda, to calculate my p0, p1, p2, right? And then to calculate my frequency. So if my theoretical frequency under my assumption of randomness matches the actual data, the actual frequency, then that means my assumption makes sense. My assumption is correct, or at least my assumption is close to what actually happened, and which is landing at random. Yeah.
All right, thank you.
And so if the probability that like the expected probability doesn't match your observed probability, then it's not random.
Yes. Yes. So like a basic intuition, right? Like there must be like more specters being hit 3 times, 4 times, right, than being hit 5 times. It's very unlikely to hit one site like 5 times, right, under the Poisson distribution. However, if your real data set provides you that there's substantially large sites, large sections being hit 5 times, then that means your assumption fails, and basically the lands are not landing at random. Maybe 1 or 2 particular sites had very important military infrastructure, and just they can throw the bombs in that 2 very important sites, and it's not at random. So Yeah, so you just compare the theoretical frequency with what actually happened. If they're close to each other, you can argue. You can argue like, what does it mean by close to each other? And I'm happy to see like your argument in the assignment. But again, if it is close, right, you're gonna define what's the meaning of close. But if it's close, then your assumption is justified. Any final questions you have?
Wait, so okay, sorry. So like for P of 5, like I got that to be a very like small number, but then like the data shows that 5 plus hits were hit in one sector. So that supports, is that what it's supporting my thing? Because it's random, because that wouldn't really make sense if it weren't random. Like or like I'm kind of confused on that. Like it says 5 plus hits were hit in only one
Yeah, so that's a good
sector.
thing. That's an indicator that that your assumption might be correct, right?
Okay, yeah, okay, yeah.
But then for like 0 or like 1 hits, like those probabilities are like larger. So like, are we still supposed to use the 1 over 5 and 576 to apply to like all of the hits? Sorry, I like worded that wrong. Like,
Yeah, because what you're gonna think about this is, first you just ignore what happened, what actually happened. You don't have the table. You just assume, well, I have a Poisson distribution, and if that is correct, then my p is 1 over 576, and my lambda is np, and I can use the probability mass function of Poisson distribution, and I get my theoretical frequency under Poisson distribution, under randomness. And then I compare, and then there's when you're gonna look at what actually happened. This is the time when you look at the table. After you have already calculated your theoretical frequency, and you compare that to the actual data, and you see if that is close to each other. If that is,
oh yeah, okay, I
no
get it.
randomness. Yeah.
Okay, okay, thank you.
And using Poisson distribution, your lambda is just NP. No matter what you're gonna calculate, no matter you're gonna calculate the probability of 0 hits, of 1 hits, of 2 hits, whatever, lambda is just N times P, and it's a constant.
So I just wanted to clarify the like reasoning for number 2, because like I just kind of did it. So you could say like, since the exponential function for one atom disintegrating is like e to the negative lambda x, and then if you're waiting for the time until first disintegration of either of them, you would just say you could multiply it together, e to the negative lambda x times e to the negative lambda x, which would give you the e to the negative 2 lambda x, and the 2 lambda you can just like kind of like separate out, and then that's your new parameter.
Yes, and the reasoning is because those two atoms are independent, so it's multiplicable.
Oh, okay. Thank you.
Yep.
Thank you, Victor.
Sure. So if no more questions, I'm gonna like stop recording and again I'll upload that to my YouTube channel. Like last week, some students say like my voice is muted, so I've tried to fix it, and hopefully this time it won't have that kind of problem. But I still post the announcement to Brightspace after I've uploaded the recording.
Thank you.
Thank you, Victor.
Bye.
Thank you.